This video is part of a series, What if the Earth is flat? Now, I was looking at the internet one day and I found this picture, and when I looked at the comments, I saw some people were complaining that it's fake. They were saying it's not realistic, and one of the first objections was the city lights. And they said that's not realistic at all. Who knows whether you can even see city lights from outer space? So I thought, well, I would look into this, and I used Photoshop, and I was able to get rid of all these city lights. And yeah, I would agree that this looks even more realistic than with those stupid city lights in the picture. But then I read further, and there was somebody else who complained that the atmosphere doesn't look realistic. That light blue edge on the shiny side of the Earth, that doesn't look realistic. So what I did is I did some color correction and I removed that. But you know what? That doesn't look realistic to me at all. So I thought I would put it back and I keep the atmosphere, because that looks pretty good. And then I saw people said that those clouds, look at those clouds, even those clouds have realistic shadows. I mean, look at that. You see the clouds, they cast shadows on the surface of the Earth, and then you have these they have a three-dimensional profile to them, because you can see the humps and the individual layers of clouds there, with shadow also casting shadows, a light side and a dark side and so forth. So I thought, well, why don't we take out that all the shadows and see what it looks like then? And that doesn't look realistic at all. Look at that. It looks like just a smudge of white on that ball. But if you don't believe me, I can tell you this is not fake, because if we look at underneath the clouds, you can see here even the mountains cast shadows, and they have a three-dimensional shape. And so with that, I mean, how can you say it's fake? If you remove those shadows, this is what it would look like. Now this looks fake. I mean, look at that. There's not even a shadow on a mountain. So before you call something fake, just because you can't see everything in the picture, maybe you should think twice and ask somebody who knows. Because what you do is, to get a picture like this, with night lights and with three-dimensional clouds and with three-dimensional mountains on the surface and with an atmosphere, and you start with a ball, right? You start with a ball that you broke up into little triangles, and then you texture that, and you build it from there, and you use shaders in a CG program. But anyway, I don't want to talk about that. What I want to talk about is plotting a map for a round Earth. And before we do that, let's just talk about the objectivity in science, because science is the intellectual and practical activity encompassing the objective systematic study of the structure and behavior of the physical and natural world through observation and independent experimental verification. It has to be objective. When you do a scientific study, and whether you are verifying something someone else did, or you're doing something new, you must be objective. That means you cannot be biased, and you must let the facts speak, and the experiments and the results speak for themselves. You cannot inject your own personal bias into that. And this is a cornerstone of science. So in the past videos, I looked at how to plot a map for a flat Earth using a stick. And in this video, we're going to look at plotting a map for a round Earth from sun angles. And you can do that using a stick as well. So we want to look at both sides of the story. If we look at how you do it for flatness, let's see how you do it for roundness. And this is not because I'm favoring one of the two. It's because I want to be objective and show both sides. So if you haven't watched the previous videos, maybe you want to do that, because I'm going to go into circles and talking about circles and angles and so forth. And I covered that very well in the first 3 videos, how even a 12-year-old can plot a map of a flat Earth using a stick, and the videos that followed that one. So go back and look at that video if you don't understand what I'm going to do, because I'm going to skip through a lot of things and not go into details that I already covered. Now, when we look at the way the sun approaches a spherical Earth, we assume that because the sun is so far away that the rays are in parallel. This is not exactly true, because if you look in the sky and you look at the sun, You should never do that with your naked eye, but if you do, you'll see the sun has a finite size. In other words, it has a top and a left and a right and a bottom. And these are a little bit apart, so the sun rays don't actually hit your eyes at the same angle. The one on the left side of the sun and one on the right side of the sun would be hitting at slightly different angles. But for the purposes of this method, that's not important, so we can assume the sun is like a point source very far away, and all the light rays enter the Earth at different angles because of the curvature of the Earth, but not because they come in at different angles. The angles are so slightly varied that we can assume they're all in parallel. And so when you make a cross section of the Earth, this is kind of what it looks like. You see sun rays enter in parallel, and if you only plot one angle at which the sun rays hit the Earth, for example 60 degrees, so this is 60 degrees and this is a cross section, then all the sun rays that hit the Earth at 60 degrees, if we only look at those sun rays, then they lie in a circle. And they come in the form of a cylinder, and that's where that cylinder intersects the Earth. That's in the shape of a circle. And so it is for every other angle. And these are the circles that we want to plot. And we can obtain them by using our stick measurements, measuring where the shadow's angle with respect to true north gives you the azimuth of the sun, and where the elevation angle is determined from the length of the shadow. Now, in the previously we plotted the shadow directly on a piece of paper, and then we plotted circles that were equal radii to the lengths of the shadows that were measured at other places at the same time. In this method, we have to do some trick. We have to be able to calculate the sun angle or obtain the sun angle somehow, either from the stick measurement or with a direct measurement. And we also need the azimuth. So you can do that again with the angle of the stick, or you can use another method to do it using a compass, or you can also use software. However, we cannot use the length of the shadow anymore just to plot. So the length of the shadow comes into the calculation to calculate the elevation angle, but we cannot just directly plot it anymore. So when we actually do an example of plotting the sun angles onto for the Earth very accurately, then we're just simply going to calculate the radius of this cylinder, and we're going to position the cylinder in a place where the sun is based on the azimuth and the elevation angle, and so if you take some measurements, you can make a table like this and then try to plot them. So this is 4 sets of measurement. The first set of measurement taken on the 6th of May, and when the sun was at 15 degrees or close to 15 degrees away from the horizon in San Francisco, it was still high up, or already high up in the air in New York. But in the morning, it was only 15 degrees above San Francisco. So this set of measurements were taken at the same time when it was 10:30 in New York. Santiago is Santiago Baja Sur in Mexico, and I'll come to why this is here a little bit later. So we plot the sun angle. This is sun elevation angle, or I just calculated them and put them in this table, and then this is the shadow angle, or the azimuth, with respect to true north, and I got this from stick measurements, but you can also use other methods. And then this is the radius of the cylinder, assuming that the Earth's radius is one unit. So we normalize everything with respect to the radius of the Earth, And instead of saying it's 6,700 or 6,371 kilometers, we just say it's 1 Earth radius unit or whatever, one unit, and then everything is normalized to that. And then the second set of measurements, I wanted 15 degrees in New York, but still visible elsewhere. So this is taken at night now. This is just before the sun sets in New York, but it's still only 3:30 in the afternoon in San Francisco. So setting in the east and much further away from setting, the further you go west. And then the last set of measurements is a special one. I wanted a very low angle. I wanted something closer to the horizon, but still reasonable. And 2.2 degrees is a very low angle. And the reason I wanted to pick this is because low angles tend to give bigger errors. It's harder to plot, harder to measure. And so these measurements were taken. Now the fourth measurement has specifically to do with Santiago Baja Sur. Santiago Baja Sur, Mexico, lies on the Tropic of Cancer, and on the 21st of June, the summer solstice, at a specific time, it was almost directly above Santiago. So here at 89.8 degrees, I believe that was the maximum angle that we were able to obtain. And in New York City, at the same time, this was the measurement. Now, you can also get the same measurements at the same time from Oklahoma City and San Francisco, get their angles and azimuths and so forth. I didn't give them in a table, but they were also taken. And so, in order to plot this accurately for an Earth, you need some kind of CAD software, or you can do it on a beach ball. But the trick is, I'm not going to explain the trigonometry here, but geometrically you have to be very accurate with your angles, and then you can plot, let's say, for one set of measurements. This is in the morning in New York. You plot these rings of elevation angle, and these are the radii of the circles. Now this involves a cosine function. Okay, I'm not going to go into that, but and then in the evening, this is a set of circles. Now the red circles represent elevation angles measured in New York. The purple circles represent elevation angles in Oklahoma City. The blue circles represent San Francisco, and the green circles represent Santiago Baja Sur, Mexico. This is on the summer solstice, was this measurement taken, and then this is the 2.2 degrees from New York, which is a small, very when the sun was very close to the horizon. It was just about on the horizon, 2.2 degrees above the horizon. And so this is on a three-dimensional sphere. You may not be able to see this clearly in the picture, but this is an actual sphere on which this is plotted. And lo and behold, we can now also just map the Earth on it, the oceans and the continents, and then we can orient it so that New York is where it's supposed to be. And if I zoom in here, then you'll see all the circles for New York intersect at New York, all the circles for Oklahoma City intersect there, all the circles for Santiago intersect where Santiago is, and all the circles for San Francisco intersected right here where San Francisco is. And this is how it should be. Also, I want to mention that the thicknesses of these lines have a meaning. This represents 2 degrees, the actual measurement, and then plus and minus 1 degrees just to account for a possible error. And what I want to show you here, and what's clear in this picture, and it comes out of the math, is that even if you make a slight an error, the error doesn't grow depending on the angle. Okay, so the error remains the same in terms of distance, because the width of these lines represent a distance error. And as you can see, all of these circles have the same width, which is remarkable. It just works so that the math actually cancels out any change in the area. The area remains exactly the same, no matter what the angle is, which is great. But not everybody has access to three-dimensional software to do this kind of thing. So I thought, well, how about we try a brute force method? We'd make some projection and some simplification, an approximation, if you will, to plot the round Earth on a flat surface, so that you can do it, so that anybody can do it with a plot, with a pencil and a compass. I mean, a draftman's compass. So again, we want to be able to plot these circles of constant elevation angle. And we can obviously, assuming that we normalize the distances to the radius of the Earth and say that the radius of the Earth is just 1 unit, we can do that and get these circles just like before. But now we want to plot it on a flat surface. So what do we plot? Do we plot the radius of the cylinder? No, we want to do something else. So take a look at this picture, and now what you see here is that if you have one angle, let's say 60 degrees, and I'm going to go back there. So this is where 60 degrees lies, and this is just as an example, is 60 degrees. But as you move on the surface of the Earth, and this is just a cross section, but at some point, there's just one point on the Earth where the sun is directly overhead. And if you deviate from that point, then you're going to get an angle. But at any moment in time, there's just one point on Earth where the sun is directly overhead. And if you deviate from that point, then the angles that are all the same lie in a circle, right? For every angle, the sun rays that hit the Earth at the same inclination angle lie in a circle. So, but we don't want to use the radius. This is meaningless on a surface. What we want to be able to do is get to the actual distance. Okay, and this may vary. This person over here measures a sun angle of 0 degrees with respect to the horizon. The sun is just setting or just rising, and so does the person over here. But the person over here sees the sun directly overhead, and then of course it changes as you move away from this position. So let's focus on the 60 degrees, just as an example. This is 60 degrees, and the angle that we see over here is 30 degrees. It's 90 minus 60 degrees, so we can generalize that. It's 90 minus whatever sun angle you measured. But the actual distance on the Earth then is this radius, or is this distance. It's a curve which follows the circumference of the Earth for a while until it's finished 60 degrees. And given a radius of 6,371 kilometers, which is sort of the mean radius of the Earth, we can measure this distance or calculate this distance as the radius times 90 degrees minus theta, or this angle, times pi over 180 degrees to convert it to radians. Because r times radians, a radian angle gives me a distance. And for a 60 degree elevation angle, then you would get 6,371 kilometers times 30 degrees times pi over 180, which is equal to 0.017453. And the answer then is 3,335.8 kilometers. So that's this red distance over here with 60 degrees and that radius. Now what we're going to do is, like I said, is we normalize it and we make the radius just one map unit, the radius of the Earth. And you can scale everything now again, just depending on what size you want to make your map. And in this case, instead of using the radius of 6,371, we use one map unit, and we do the same calculation, and we get 0.5236 map units is this distance. So now, what if we just plotted this distance as the radius of a circle. So the actual distance on the planet is what we're going to plot as a circle. And so this is how this projection works, is we flatten all this, but we keep the distance exactly right. And if we do that with the same data, and we just calculate new radii, okay, now the radius becomes, like I said, r times 90 minus theta times pi over 180, and that's what you get for the same data. And these are the circles that we plot. Now this line, the red is again New York, and in this case New York would be right here, and this is the position of the sun given a flat surface. So we've bent everything flat now, and where the sun is, we're bending all those distances on a flat surface, and we plot them on a piece of paper. So it's colored here. Again, New York is red, Oklahoma City is purple, Santiago Baja Sur is green, and San Francisco is blue. And if you had a stick planted here, it would cast a shadow in this direction. So we extend that shadow this direction by that distance that we just calculated for New York, and we get the position of the sun. So this represents on the map where the sun is directly overhead. Everything scaled down. And if you take the measurement in the evening, this is what you get with using the stick's angle as well. And at 2.2 degrees, you get a bigger set of circles further away from New York. And sun is about to set in New York, but it's still up in San Francisco and Oklahoma City and Santiago. And then on this, if we plot them together, this is the morning, this is the evening, this is almost setting in New York. And there's a fourth set, which is from Santiago Baja Sur. And now, if we zoom into these triangulating elevation angle circles, and we look at where they intersect, lo and behold, we have each of these sets intersect at the same point. Now, again, the thickness of the lines represent plus minus 1 degree error. And in the center of this, I don't know if you can see it, but there's a white line, and that represents the exact angle. So New York's lines intersected over here, Oklahoma City intersected here, Santiago over here, and San Francisco over here. And this lies exactly in the shape that we expect. So if you look at the map, you will see that these three lie almost in a straight line, and then San Francisco lies off. So you have sort of an inverted L-shaped distribution here. And now, I must say that if you look closely, you'll see that there is a discrepancy. They don't intersect 100%. The thickness over here should be one line if they intersected, and over here as well, and over there as well. So they don't intersect perfectly. Why is that? Well, when you try to peel an orange, and you take those peels, you try to reassemble them on a flat surface, you're going to have gaps, right? You're going to have gaps, and if you took slices and you open them up on a flat surface and try to reassemble them there, you're not going to find that you can stick all these pieces of skin back together. There are going to be gaps between, and there's going to be problems. So this also happens when we do this. It's an approximation, it's a brute force method, and I'm actually surprised that it came this close. I thought that the error would be much bigger, but intuitively, but my intuition was wrong. It did turn out to be to give a fairly good triangulation for these cities. Now, these distances may be, quite large. We're talking probably 50 to 100 miles that these span across, but it's still very, very good. And so this method I would recommend also to to try to plot and verify that you can plot a map for a round Earth if you don't have the CAD software to do it on a sphere. So you can just do it directly onto a piece of paper. And next time, in one of the future videos, I will do the example for plotting a map of a flat Earth. In the meantime, I am curious to know if anybody has actually tried to map a flat Earth using the stick method. Since I started publishing these videos, I haven't seen anybody do that. I have not seen any interest in it. I haven't seen anybody actually attempt to plot a map for a flat Earth, even though I know there is no real map for the flat Earth. They constantly show Gleason's map from over 100 years ago. So why not? Why wouldn't anybody be interested using the technology that we have to plot a map for a flat Earth? So I challenge you guys. I challenge and encourage you to get some friends together and plot a map, or try to at least get something started to get a map for a flat Earth. Thanks for watching. What if the Earth is flat?